differential form. So our next aim will be to convert this equation to this. So let's do this. So it will be a kind of reverse process which we have followed. So we have integration of b dot dl equal to mu naught, it's not an integral right in the right hand side, so I have to rub it. So you have mu naught I plus mu naught epsilon naught times del or d phi e upon dt. So changing electric flux gives you current. So there may be any region where both types of current may be present. That is, there is a conduction of charge, and there in that region electric field also changing. In that case, you have to consider the currents with both the factors, and the combined effect of that taken, then you will be able to calculate the total magnetic field, because magnetic field depends on both the things, the flow of charge, that is the current, conventional current, and if in that region the electric field is changing, that changing electric field produces a magnetic field. So you have to consider both the things. So this is what was missing in Ampere's law, and which Maxwell modified and said that not only current is responsible for the production of magnetic field, rather the changing electric field can also produce magnetic field. There is no current present in any space, but just by changing the electric fields we can produce magnetic field. So this was the new kind of thing introduced after Ampere's circuital law. So our aim is to convert this equation to its usual form. So you must take a curl of this. So you will have to write this, the left hand side, as the curl of this. So we have to take del cross B times dA. So in this way you have converted the left hand side. Now for the right hand side you have to find these two terms. Now for I term you will have to write it as mu naught integration of I will be written as j dot dA. By definition I equals j dot dA. So this is the surface integral. Now the third term, which is mu naught times epsilon naught, and this will be the different term. So you have mu naught times epsilon naught, and this d phi by dt we are calculating it separately. Just calculate it separately. Now d by dt of this phi e. So we have to write it as phi e, as you can write it as the integration of E dot dA. So we have to replace, we can swap the integrals, we can take this derivative term inside. So this will be equal to del E over del T dot dA. So this is your d phi upon dt term. Now write it here. So you have del E over del T dot dA. So now all the integrals are done with respect to this area. This is also area, and this is also area. So simply you can write that del cross B equal to mu naught times J plus this mu naught epsilon naught del E over del T. So you can see how easily we have got the differential form of Maxwell's Maxwell law from the integral form. So in this manner, the mystery of how the current is flowing inside a capacitor and in between the plates of the capacitor, how a magnetic field is generated, was solved by Maxwell. So in this manner, one major problem of finding the magnetic field inside the in between the plates of a capacitor was solved. But this led to another problem which Einstein visualized after seeing the Maxwell's law. So we will have to do some mathematics to understand how Einstein was able to figure out that there is some problem with the Galilean transformation, and for Maxwell laws to be true, the special theory of relativity must be a requirement. So we have to justify all these things. So for that we will need to understand how we can derive, how we can write the electromagnetic wave equations from Maxwell laws. So our next step will be how to write electromagnetic equations from Maxwell law. Actually, in the start, it doesn't seem to be an electromagnetic equation. Its form was telling that it must be representing some wave. So we will come to that. So let's start how we can get from Maxwell's law the electromagnetic wave equation, and why we are telling that equation as electromagnetic wave equation. So let's see. So before we proceed further, let's write all the four Maxwell equations. So first is del dot E equals rho upon epsilon naught. Second is del dot B is equal to 0. Third is del cross E equals minus del B over del T, the Faraday law of induction. And the fourth is del cross B equals mu naught times J plus mu naught epsilon naught del E over del T. So we will take a curl of these two equations and let's see what we get. So first we will take the curl of the first equation, the third equation. So if we take the curl of this curl del cross E, then this should be equal to del cross minus del B over del T. Now we will use an identity that this del, now we have to write a cross here, del cross F, where F is any vector field, then this is equal to del dot F minus del 2 f. This is sometimes called Laplacian operator. So some people might confuse that this del over del 2 times must be equal to del 2. Like if you take the derivative of some function dy dt of dx by dt, then you get d2x over dt square. It's not like that. If you calculate, if you really find, take a vector and just take the divergence and then take the divergence, and if you multiply just two divergence term and then operate it on the field, then you will get different things. So they are not same. So this is the identity which we will use. So if you take the curl of electric field, then from the identity in the left hand side we must get del dot this del dot E minus del 2 E equal to, now we will swap the derivatives. So minus del by del t of del dot b. So this was first del over del t operation was done and then del. Now we have just swapped, so it can be done because they are commuting in nature. So now what we will do here, that we will assume that in free space if there is no charge and current are present. If in free space no charge and current are present, in that case this charge density, there is no accumulation of charge, there is only free empty space, so rho must be 0. And if there is no charge, then there is no possibility of flowing any charge, so there must be no current in that space, so the current density must also be 0. So if we assume this case, for example, light coming from sun to earth, in between earth and sun we can assume that there is no medium present, so there is no charge between them and there is no current. So for that case, if you assume light to be a wave, because it was suggested from the Young's double slit experiment that light has the properties of a wave because of the interference patterns observed from the Young's double slit experiment. So it is a suggestion from Young's double slit experiment that light can be a wave. So if it is a wave, then what kind of wave it is? So we are estimating its kind from electromagnetic theory. So just take that there is no accumulation of charge and there is no current, so current density is also 0. So this term del dot E, now del dot E is what? Rho upon epsilon naught. So you have to write it as del dot rho upon epsilon naught minus del 2E equal to, actually there is a mistake here, it was a cross term, so it must be a cross. So we have swapped it, but it does not changes from cross to a dot, so it must be a cross term. So now you have this del cross B term, so it must be minus del over del t, and now we will write the del cross B term from our fourth equation. Now from the fourth equation, you know that this term is 0 because this j is 0, so this term must be 0, so we will only write this term. So just write this term del cross B equals mu naught epsilon naught del E over del T. So what you get is del 2E with a, because these two minus signs will be cancelled, so del 2E is equal to mu naught epsilon naught times del 2E upon del T square. There is one derivative with respect to T, and again taking the derivative with respect to T gives you del 2E upon del T square. Now this thing always surprised Maxwell, that mu naught into epsilon naught exactly gives you 1 upon C square, and this indicates that if light is wave which is flowing with this C speed, then this we are coming to that. Just we have to write this form. Now you write this as 1 upon C square taken in the left hand side, 1 upon C square del 2E upon del T square. So you exactly get an equation which looks like a wave equation. In every wave equation you have the form as del 2 phi minus 1 upon V, the speed of the wave in that medium, into del 2 phi upon del T square equal to 0. This is the usual form of a wave. Now why in the electromagnetic equation, just by taking a curl of the curl, you are getting a type of equation which is similar to wave equation, and strange thing is that you are not getting a speed term, you are getting epsilon naught mu naught, but when you multiply it you get 1 over C square term, there must be V square. So you get a 1 upon C square term. So this suggests that this must be the equation of wave whose speed is C, and it's the speed of light. So it can be an equation, wave equation for light. So similarly for the fourth equation, we will take the curl of this equation. So the curl del cross B, this should be equal to del cross. Now you don't need to write these two terms because J is 0, so this term already goes off. This term is 0 because J is 0 for a case of vacuum or free space where there is no charge or current. So you have to write just this term. So mu naught epsilon naught del E over del T. So now the left hand side becomes del dot B minus del 2B from our identity, this identity, and the right hand side you have mu naught epsilon naught del by del T of the swap of the differentials, so they are commutative. So del cross this E term. So this term from the second law it is 0, from the second equation it is 0, so only this term survives. So del 2B is equal to, now what you have here, del cross E, and from the second equation del cross E is equal to minus del B over del T. So you have to write it. So you have to write it in this manner, mu naught epsilon naught del over del T, and just replace this del cross E term from the third equation as minus del V over del T. So it's just like a repeating thing. You take the curl or dot, each time you take a curl, from one of the equation you get another equation. So just like in this case, so you will get here that minus del 2b equals mu naught epsilon naught, and there is also a minus sign, this minus sign, del 2b over del t square. So from here you get that del 2b minus, now you know that this epsilon naught mu naught term becomes 1 upon c square. So c square del 2b upon del t square. So for the magnetic field also you get the same structured, same kind of equation, and these two equations are of the same form of a wave equation. So this suggests that these two equations can represent an electromagnetic wave, or from the Maxwell equations we have derived these two equations. So these equations must be the wave equations of light, because what instead of v square we are getting here c square, because c square equals 1 upon c square equals mu naught time epsilon naught time. So the velocity of light is coming from these two terms, mu naught and epsilon naught. So these two terms, epsilon naught and mu naught terms, which are coming in the equation and which gives you 1 upon c square, which suggests that it's the equation of wave equation of light. So in light there may be changing electric and magnetic fields. Changing electric fields may generate magnetic field, and changing magnetic fields can generate electric fields. So it's a vice versa thing. And now the problem is that if you see it closely, then you find that the velocity c square is depending on these two terms, and this mu naught and epsilon naught terms are always constant throughout the space. Unless you change the medium, like in water or in glass, these terms can change. But for empty space, everywhere space has same kind of property. So this epsilon naught and mu naught are not changing. So for a rest observer, for an observer who is at rest, he measures the properties of a space, the epsilon naught and mu naught. And for an observer who is moving with some velocity, will he measure that in a space he is observing epsilon naught prime and mu naught prime? So it's not true. Whether you move or do not move, you measure these properties at rest or in motion. You always find that the two things are same. That is, the forces between two charges is independent of the fact that you are in motion or you are at rest. The Coulombic attraction between the two will not change, because this epsilon naught term does not depend on how you are moving. Similarly, the magnetic field produced by a magnet doesn't depend on how you are moving, because this magnetic field is given by this mu naught term, the strength of magnetic field, and this mu naught term must be independent of the observer, because these are the properties of empty space and it is constant everywhere. So the speed of light should also does not depend upon how an observer is moving. So when you observe this closely, then you find that mu naught and epsilon naught are the properties of space, empty space or vacuum, and it doesn't depend on how an observer is moving. So because the products give you the velocity of light, so whether you are moving or you are at rest, you will measure that a beam of light will always move with the same velocity, or you can say that the speed of light depends on these two parameters, and these two parameters are independent of the observer, that is independent of the velocity of observers, because these are the properties of space. So c square term must also be independent of the motion of the observer. So we can say that the speed of light must be independent of the motion of observers. So in this way, Einstein said that the Maxwell equations must remain invariant in these kinds of in transformations. But the Galilean transformation, in Galilean transformation we see that the form of these equations, we have seen in our earlier lectures that the form of this equation changes in case of Galilean transformation. So Galilean transformations are not appropriate kind of transformation for electromagnetic theory to work. So there is a need of some different kind of transformation which can accommodate the laws of electromagnetism. So those kind of transformations were called Lorentz transformation, and in our coming lectures we will be discussing Lorentz transformation equations. The wave equations which we got from Maxwell equation suggest that the speed of light must be constant for all observers, and this assumption gave rise to the special theory of relativity, and this assumption also gives you the energy and mass equivalence relation, that is E equals mc square. And so Einstein being a theoretical physicist, he depended on these equations to tell that the speed of light must be a constant, otherwise it will not satisfy the laws of electromagnetism, and he even doesn't needed the confirmation which came from Michelson's Morley experiment. So it was just from theory. You can say that for Einstein the special theory of relativity was lurking from these equations, and Einstein was the first person, you can say that, who was able to see that these equations are giving you the results which says that there must be a different kind of transformation which we need to find. So our next aim would be to understand those kind of transformations and how we can find those kind of transformations, that is the derivation of the Lorentz transformation equations. This constancy of the velocity of light also suggested that if this velocity of light depends upon these two factors, mu naught and epsilon naught, and this speed is also constant throughout the space, because for all observers they are observing the same speed, and only by assuming this we will be able to retain the form of these Maxwell these electromagnetic wave equations. So so it seemed that if this speed of light c is same for all observers, then there must not be any absolute reference frame like ether. If ether is present, then all the things are moving with respect to ether. So but we are seeing that for all the observers the speed of light is same. So speed of light is independent of the speed of observers, and this can only be justified by saying that there is no existence of ether, that is, there is no absolute frame of reference. So in this manner Einstein rejected the theory of ether, and in empty space light moves with this constant speed, and anything moving in that empty space measure the same speed of light. And someone who suppose in a spaceship is going with a speed of light, and another spaceship which is going with a speed of light. Assume that there is some kind of a spaceship which exists. So with respect to B, the speed of this spaceship with respect to B, the speed of this spaceship must be 0, because you just simply subtract c minus c equals 0. But this was not the case. If anything moving with a speed of light, then it will move with the speed of light. It will seem to move with the speed of light for all observers, whether it doesn't depend on with how much speed the observer is moving. It will always measure if he starts with if he changes his speed from c, or it decreases with speed v, or it moves with any velocity, any speed, he will always measure that the speed of this spaceship is c. So the speed, anything which is moving with a speed of light, so will always be measured to be moving with a speed of light irrespective of the frame of reference, and this is called the special theory of relativity. So from the next lecture we will be discussing the Lorentz transformation equations and how it affected the electromagnetic theory, how electromagnetic theory is invariant in Lorentz transformation. So please like our video, share our video, or if you have any kind of problem, then you can ask in the comment section. And thanks for watching.